Hello again. This is Introduction to Machine Learning, CS 480 and 680, as taught at the University of Waterloo in fall 2024. And this is lecture 9b, where we're going to be discussing Gaussian processes. So this is the conclusion, second part of what we started in lecture 9a the last time. Um, so yeah, quick recap of what we covered in lecture 9A. So we explored, our focus was on Bayesian updating to refine our beliefs about a parameter by combining prior knowledge with new data. So we started with an example of the beta distribution, where we use a distribution over a prior belief, the grade curve, and then we updated that with observed data in the dashed red line to obtain a new posterior distribution in the teal curve. And so we saw that this process gave us a more confident estimate of the parameter value, and then the posterior reflects our updated belief after seeing the data that is used at where we use Bayes' rule. So we applied the same concept to linear regression, where we moved. Yes, we applied the same concept to linear regression, where we had a set of fixed nonlinear basis functions. So the true underlying function was in gray, and then the MLE estimate was in blue. Ridge regression shown in orange, and then the MAP estimate, maximum a posteriori estimate, that we obtained by imposing a prior belief on the weights, that's shown in purple. We also saw that ridge regression can be interpreted as imposing an isotropic Gaussian prior on the weights. And then finally, we talked about sequential Bayesian updating, which allows us to incrementally update our posterior as new data arrives. Specifically, the prior times multiplied by the likelihood produces a new posterior, and then that posterior becomes the new prior for the second time around. So this last result could be really useful in online learning settings where we want our model to adapt continuously without the need to retrain from scratch. So yeah, let's revisit the data set that we relied on in part A. So we had data points representing energy generated over the time on a particular over a day. And so the x-axis was the time of day, and then the y-axis was the energy generated in kilowatt hours. And then the observed data points were these black plus markers here, and then the true underlying function was something like this smooth magenta curve. And so crucially in part A, we actually knew what the form of this true underlying function was. We had access to what those set of nonlinear basis functions were. Yeah, in general, that doesn't really tend to happen in real life all the time. So very often we don't know what the form of that model should be, and sometimes when that's the case, this function is something that we need to discover. So we could imagine trying to fit a linear regression model to this data, but with only a straight line to play with, there's no way it could capture the ups and downs of this function. It would give us a linear fit that would go near these points, but it would not get the right shape of this function. It wouldn't get that right at all. So we could specify a set of basis functions to span a space of more flexible nonlinear functions. But the problem there is that if we predefine a set of basis functions, we're making assumptions about the form of the function we're trying to learn. And there's no guarantee that our chosen basis functions will be capable of representing the true function. So ideally, we would like a model that is more flexible, and would allow us to capture any underlying function that passes through these points without being constrained by preset basis functions. So in this, so whereas in part A of the lecture, we talked about incorporating prior knowledge and quantifying uncertainty, in the second part B, we're considering kind of the opposite situation where we really have very little knowledge at all to solve this regression problem. Specifically, we don't even know what form of the model, what set of basis functions we can use. So this exploring this question, taking it seriously, is going to lead us to a very general framework called Gaussian processes, which is the title of the talk today. And this is not going to assume any specific parametric form for the underlying function. As we get more data, it becomes flexible enough to capture essentially any function that goes through those data points. All right, so before we talk about okay, so before we talk about the nuts and bolts of Gaussian processes, um, let's start by just looking at its behavior after we've trained it. So on this slide is a picture from a figure from the probabilistic machine learning textbook, specifically out of section 17.2. So the plot depicts some data points shown as black X marks, and then the true underlying function that we want to learn is hidden. So the horizontal axis represents input values, and then the vertical axis represents the corresponding outputs. And of course, we're trying to do regression, some nonlinear regression on this data set. And our goal is to uncover the function that best describes this data. And so what the Gaussian process does is depicted by both the line and the shaded area in blue here. So the blue curve on the graph represents what's known as the mean function that the Gaussian process has learned. So we can see that it closely follows the data points. And then the shaded region here shows the uncertainty or confidence interval around that mean. Specifically, the shaded area represents plus and minus 1 standard deviation from the mean function at any one point. So we can see that where there is data, where the function is near those points, the uncertainty is low. So the shaded region is quite narrow. And this is because the Gaussian process has seen these values and it knows that the function has to pass through them. But then in between these data points, like in this interval here, the uncertainty increases. So the shaded area widens. And it's because the model isn't as confident about where the function should go between those known values. So the Gaussian process expresses this uncertainty using a Gaussian distribution at each point along the input axis. And so what makes the Gaussian process so powerful is its ability to learn distributions over functions, actually. So it gives us a flexible way to do regression without assuming a specific type of function, like a polynomial or a sine wave or a sigmoidal set of basis functions. So this is why we call these Gaussian processes non-parametric models. They don't restrict us to any particular type of function. Instead, they let the data guide the form of the function. So this makes Gaussian processes incredibly useful for when the relationship between when there's unknown relationships in the data. Okay, so now let's get into the details. So if you were listening closely, you might have noticed that in the last slide, I said that Gaussian processes learn a distribution over functions. That's not something we have really heard about before. So let's contemplate what that means. What's a distribution over functions? Okay, so as our starting point, let's talk in lecture 9A, we talked about the posterior distribution of the weights in Bayesian linear regression. So we weren't just finding one set of weights that defined a single function. No, we were working with a distribution over possible weight values. And that distribution, which we called the posterior, that told us which set of weight combinations are more probable given our observed data. Okay, so every sample we drew from this posterior distribution corresponds to one specific set of weights, and those weights define one particular function that mapped the inputs to the outputs. Okay, so yeah, let's go through a specific example. So if we look at the leftmost plot here, this depicts the posterior distribution over the weights W0 and W1, which are the intercept and the slope of the linear model in the case of a single input feature. So the color indicates the probability density. Brighter or warmer, where the yellow colors represent high probability selections of the weights. And then the dark colors are low probability regions. So when we draw a sample from this distribution, we're selecting one point in weight space. And so let's consider this gray cross here as one such sample. So now we've got this gray cross gives us one sample from weight space, which in this case would correspond to a bias of around 1, and then a slope of -1. So this sample defines a specific line with a slope and an intercept that correspond to the sampled weights. And so we can actually sketch that here. So we've got a bias, an intercept of 1, and then a slope of about -1. And so this line now represents one possible function that could map our inputs to our outputs given the observed data. This is one of many potential lines that the model believes is possible. And so each time we draw a new sample, we get a different set of weights, different line. But anyways, in this particular case, we would feed in an x value of about 3.7, and this function would evaluate that input to be about -2.3. So we've got a function value of -2.3 for a particular input of 3.7 and a particular sample from weight space. But yeah, that's just one potential out of this is just one potential function out of the many that we could have generated from this posterior distribution of the weights. So yeah, we can repeat that sampling process. So each time we draw a sample from this distribution, we'll get a different set of weights, and then we'll be able to define a new function, and then we'll get a new evaluation of that function for the same input. So yeah, in the middle plot of this animation, we can see what happens when we draw multiple samples from the distribution of the weights. We're building up a collection of different lines, each corresponding to a unique function. And so these lines show how the function can vary based on different samples of the weights. But here's the crucial part. So because each set of weights came from a Gaussian distribution, were drawn from a Gaussian distribution, the resulting function values over here, they're also going to follow a Gaussian distribution. So this is a key property. Since any linear combination of Gaussian distributed variables results in another Gaussian distributed variable, the function values y are themselves Gaussian distributed. So yeah, the plot here shows the distribution of function values for a single evaluation point of x of 3.7. So yeah, every single one of these pink dots are function values obtained from distinct samples from weight space. but the same input value x. So we can see as the distribution builds up, they're centered, they're clustered around a central mean about about zero because this particular probability posterior distribution over the weights is close to zero bias as well as zero weight. But then it spreads out. It spreads out as we get further and further away from that mean. And so if we kept sampling, if we sampled forever, we would recover the parameters of a new one-dimensional Gaussian distribution centered at some mean and variance. Okay, so if the distribution over function values for a single point is a Gaussian, what about the relationship between the distribution over function values at two different input points? So if the function value at one input is Gaussian, then at one input is Gaussian, then the function value at the other input must also be a Gaussian. So for example, if we picked some x of 4.7, and then we found out the distribution over function values y, given the posterior distribution over the weights, then we would see that a Gaussian, for that input point. And similarly, if we selected another input point, say negative 3.3, then we would be able to draw a Gaussian over function values for that input point. And so if we considered those two together, the joint distribution of these two values is also going to be Gaussian, but specifically a multivariate Gaussian now. And so yeah, the 3D plot here shows this joint distribution over function values at two different inputs, x1 and x2. The horizontal axes represent the function values x1 at x1 and x2, and then the vertical axis represents the probability density of the joint distribution. And so the peak in the center here corresponds to the mean values for both inputs. And then the spread of the surface indicates the uncertainty or variance in these function values. And so because the joint distribution is Gaussian, it has this nice bell-shaped contour that smoothly falls off from the peak. And yeah, as we saw before, the joint distribution is constructed by multiplying the individual distributions together, which are shown by the black curves behind this surface plot. And so this concept is going to generalize really nicely. So we can extend this to describe joint distributions over function values for any number of input data points. So in this case, I've got two input data points, but this can generalize to to 10, 100, 1,000, to a joint distribution of function values for any number of input points. Okay, so this illustrates the definition of a Gaussian process. We're dealing with a probability distribution over functions such that the set of function values y evaluated at any set of arbitrary points, so x1, x2, up to xn, jointly have a Gaussian distribution. So in other words, if we were to choose any collection of points and look at the function values at those points, those values will follow a multivariate Gaussian distribution. So that's what we mean by a Gaussian process. Okay, so we can formalize this thinking now. And so the really nice thing about Gaussian processes is that the joint distribution over these function values is completely specified by the mean and the covariance. It's a Gaussian distribution. And so the only two pieces of information that we need are its mean and its covariance matrix. Okay, so let's see if we can figure out what that is, what those are for our linear model with the fixed set of basis functions. So in that model, we had y of x is equal to w transpose phi of x. And so we could then specify the vector of outcomes y, given the matrix of features phi and the weight vector. And let's also now assume a prior distribution over the weights as a zero mean distribution. And because we typically don't have prior knowledge about the mean of function values. And then we'll also assume that the covariance matrix is a diagonal matrix. So this I here is the identity function. Identity matrix, which is zero everywhere except along the diagonal. So the covariance matrix is going to be a diagonal matrix, but then the elements along that diagonal are specified by this precision quantity alpha, which is inversely proportional to the variance of the weights. Okay, so the mean of y, the expectation of y, this is going to be phi times the expectation of the weights. But we've set the expectation of the weights, the mean of the weights, in our prior to zero, so that this mean of function values is also going to be zero. So now moving on to the covariance. By definition of covariance, and because we've assumed the mean of y to be zero, this covariance is simply the expectation of y transpose. And we can expand this by using the definition of y in terms of our matrix phi and the weight vector. But the expected value of W transpose, that's only going to have the effect of scaling the resulting covariance matrix by our assumed precision. Because we assumed that the covariance of the weights was the identity function. And so, yeah, we're multiplying the identity function by phi transpose. That's not going to do anything. And the only thing that's going to have an effect is the precision quantity alpha. And so we're left with phi t times the precision quantity. And this itself is a covariance matrix that actually defines the kernel matrix for a particular function mapping. That is, K is the elements K, the elements ij of matrix K are given to us from a kernel function of xi and xj. And so that's going to capture the similarity between these two inputs points, xi and xj. The similarity between these two input points, xi and xj. So the covariance is alpha inverse times the kernel matrix. So this model gives us a specific example of a Gaussian process, which I said before is a probability distribution over functions, such that the set of function values evaluated at an arbitrary points jointly have a Gaussian distribution. The mean gives us the average value of the function at any point, but because that's zero in our case, the covariance matrix completely specifies the joint distribution. And that can be computed through the kernel, which tells us how function values at different points are related. Yeah. Okay, so let's now see how we can apply Gaussian process models to linear regression problems. So to do this, we can begin by considering that our observations, T sub I, are generated independently from an underlying true function, Y sub I, plus some random noise, epsilon I. And what we're ultimately interested in is the distribution of the target values T, taking into account both the prior on the underlying function Y and the observed data. Okay, so let's assume that each observed value T sub I is distributed around Y sub I with some noise variance. And so let's further assume that the noise is independent for each data point. So the joint distribution of target values T conditioned on the value of Y, that's going to follow an isotropic Gaussian. with a mean centered around Y, and with a covariance matrix that is the identity matrix with diagonal elements scaled by this quantity beta inverse. And then beta itself is going to be the precision of the noise. So the inverse of the noise variance in our noise model. The marginal distribution over Y is also a Gaussian whose mean is 0, and whose covariance matrix was that kernel matrix K scaled by alpha inverse. And so to get that distribution over T that we're really interested in, we need to integrate out the effect of Y. And so this is going to result in a new distribution for T that's also a Gaussian, but with a covariance matrix C, and that's centered around the 0 vector. And so each element of the final covariance matrix C is going to have two components. The kernel matrix, the kernel evaluation of Xi and Xj scaled by alpha inverse, and then a noise term scaled by beta inverse. And so the combination of these two terms reflects the fact that our uncertainty about T comes from both the underlying function uncertainty and the noise in our observations. And so to get this result, we've exploited a standard rule for combining covariances of our Gaussian distributions. So the resulting covariance matrix for T is simply the sum of covariances for of the two sources of randomness. And so in our case, C includes both the covariance of Y, which is defined in terms of the kernel matrix K, scaled by alpha inverse, and then the noise covariance of epsilon, which is represented as beta inverse, where this delta term is non-zero only when I is equal to J, as is the case for that diagonal matrix. Okay, so so far we focused on modeling the joint distribution over the observed training points using the Gaussian process, which allows us to describe how the known points are related to each other. But ultimately, our goal is to predict the value of the function at a new test point that we haven't seen before. So let's now discuss how we can extend the Gaussian process framework to make predictions at new, unseen data points. So we're not going to get into the weeds here, but it turns out that this is done by augmenting the existing covariance matrix to include this new data point. And so the idea here is that if the Gaussian distribution holds for n training point, it should also hold for n+1 points where we can kind of sneak in that new test point. Okay, and so the way that we incorporate this test point is by augmenting the existing covariance matrix to account for the relationships between the test point and the training data. So that's going to result in a new, larger covariance matrix. And so this new larger covariance matrix is C of n+1. And it contains a few components. So the original covariance matrix, C sub n, then the covariance vector, K, which is going to give information between the test point and each of the training data points. So that'll be a column vector, and then we've also got to add the transpose of that to get a row vector. And then there's also a single value C for the point itself. So a bit more about these extra components. So the vector K is a column vector that captures the pairwise interactions between the new test point x of n+1 and each of the training points. So x of 1 and x of n+1, x of 2 and x of n+1, and so on and so forth. And then the value of C is the variance of the new test point, and then also incorporating uncertainty about this point. And so, yeah, the key takeaway here is that, with this this augmented matrix, we've absorbed the test point into the model. And so the augmented matrix C of n plus one, this captures all the necessary relationships. So this is what's going to make it possible to extend our Gaussian process model from the known points to the unknown ones. So that augmented covariance matrix actually tells us everything we need to know in order to make predictions. So we're going to be able to directly compute the mean and the variance for our prediction of that new test point. So in this course, it's going to be enough to know that there's closed form expressions for the mean and variance of the distribution over target values. Specifically, so we know that the distribution over target values over that distribution over that new target test point, given the existing training data, we know that that's going to follow a Gaussian distribution with some mean and variance. And so the mean is so that's going to represent the expected value of the function at the new test point given the observed data. And this is calculated as K transpose the inverse of Cn and then times T, and then where T is that vector of observed values of the training points. So it turns out that another way to write this is as a linear combination of the kernel values between the test point and each of the training data points, weighted by a set of coefficients derived from the training data. These are the coefficients of the training data are given by this equation down here. So the mean prediction is a weighted sum of the observed values where the weights themselves depend on how similar the test point is to each of the training points. And then the variance, that's going to tell us about the uncertainty in our prediction for that new test point. It's calculated as C minus K transpose inverse of C times K. And then K is that vector of covariances between the test point and each of the training points. And then CCN was the covariance matrix for the training data. So to give some intuition here, when the test point is really close to one of the training points, the values in K are going to be large. And so the variance, and because we're subtracting this value, the variance then the variance or the uncertainty is going to be low. So we're going to have greater confidence in our prediction when our test point is close to existing training data. Okay, so that was a lot of math, but to provide some intuition for the overall process we followed, let's take a look at this figure. So this graph provides a visual representation of the process we just went through. So the red ellipses show the contours of the joint distribution over a single training point, T sub T1, and then a single test point, T2. And so when we condition this joint distribution on a single training data point, the value of T1, which is represented by this vertical blue line here, we're looking at the distribution over T2 for a particular value of T2. And so we're effectively looking at a slice of the joint distribution at this particular value of T1. And so along this blue line, the conditional distribution is going to follow this green curve. And that's going to have a mean value of x, of the mean of x2. Quick summary before we move on. We absorbed the new test point by augmenting that covariance matrix. Then we computed the mean and variance of the predictive distribution at the test point using that augmented matrix or parts thereof. And so within this framework, we can predict the function value at any new point. So we talked a lot about Gaussians today. There's the posterior follows a Gaussian, function values are a Gaussian, or they follow a Gaussian. Our noise model was also a Gaussian. We haven't said much yet about the kernel itself. Do we have a choice there? Does that also need to be a Gaussian? And so it turns out that no, we can actually use many different kernel functions in a Gaussian process regression, model. The kernel function is important because it defines our notion of similarity, specifically by defining the properties of the covariance matrix K, and that controls how function values are related to each other at different input points. The kernel expresses the idea that points that are similar, the corresponding function values are going to be strongly correlated. And points that are dissimilar, the function values are going to have weak correlations. And so that exact notion of similarity depends on that choice of kernel function. There are a few restrictions. The kernel function has to be a Mercer kernel, so it must be positive semi-definite to ensure that the covariance matrix K is positive definite. And then each kernel can have its own hyperparameters to further influence the behavior of the functions. So that these plots here show two different kernels. So on the left is the Gaussian kernel, or the radial basis function kernel, also known as the squared exponential kernel. So it's going to result in smooth curves because the kernel causes high covariance for nearby points. And on the right side here is the curves generated using the exponential kernel. The exponential kernel takes the absolute distance between points instead of squaring it. And so this kernel shows a lot more jagged and fast-varying curves compared to the Gaussian kernel. What's really interesting is that you can actually think of linear regression with fixed basis functions as a special case of a Gaussian process. So this happens when the kernel function, k of x and x prime, is defined in terms of a set of finite basis functions. So in this scenario, the Gaussian process and linear regression are actually two sides of the same coin. So you can either work from the parameter space perspective using linear regression, or from the function space perspective using a Gaussian process. The predictive distributions are going to be the same. So when you set up your kernel function to represent those fixed basis functions, the Gaussian process framework reduces to the familiar linear regression results. But what's kind of tricky is that despite these two solving the same problem, there are computational trade-offs between the function space view using Gaussian processes and the weight space view using fixed basis functions for regression. And so the core difference lies in the computational cost of the matrix operations, especially when handling large data sets. And so when in Gaussian processes, the most expensive step is inverting that n by n covariance matrix, where n is the number of training data points. So yeah, in this inversion step for the most standard methods, it's going to have cubic complexity with n. So this is going to become very expensive as the number of training data points increase. In contrast, in the fixed basis function models, we also need to invert a matrix, but we only need to invert an m by m matrix, and then m is the number of basis functions. So it's going to cost us, that's also going to be of cubic complexity. But typically the number of basis functions is smaller than the number of training data points, in which case using fixed basis functions would be more computationally efficient. So yeah, in the big data regime, Gaussian processes can become computationally prohibitive because that's cubic scaling with n. So while Gaussian processes give us the flexibility to use rich infinite dimensional spaces and to not have to specify those basis functions up front, you'll pay for it if the data set gets too large. So yeah, if m is small and manageable and you actually know the basis functions, then it might make sense to to use known basis functions, but if you need the flexibility and more complex kernels, and you don't have too much data, then Gaussian processes in the function space view might be the better fit. So yeah, there's strengths and limitations for each approach. All right, so that brings us to the end of part B, as well as the end of lecture 9. Um, and so yeah, do a quick summary now and identify what you can expect to be able to go out and try for yourself with what we talked about. So we applied Bayesian updating to determine the posterior distribution of parameters using the likelihood and given a prior. So looked at that for a beta distribution and then also for a linear regression model. We also talked about how to design suitable priors for Gaussian models that could reflect domain knowledge and serve as a form of regularization. So yeah, we talked about a couple ways to had some not so informative priors of things like just assuming that weights would be around zero with some variance. We also looked at some more intelligent ways to impose to say that no, certain weights should fall around here, and we're more confident about some weights than others. So yeah, ideally you should be able to go and formalize represent this prior knowledge if given something like that. If given a domain knowledge, if given some description of domain knowledge. We also then encountered maximum a posteriori to actually incorporate this representation of prior beliefs into a regression model. And we talked about how it's safest to use maximum a posteriori and to impose these priors when we're in data scarce applications and we really do know something about the problem and we have that domain knowledge. We made an interesting connection between ridge regression and penalizing large weights as imposing a prior belief on the distribution of the weights. And we also talked about, we also covered Gaussian processes. And specifically, we encountered expressions, closed form expressions for the mean and the covariance of the predictive distribution. And so, yeah, if you were given a particular kernel function, then you should be able to sketch exactly where the mean would be, and then what the uncertainty would be around that mean for a small training data set. And then last but not least, we talked about how Bayesian linear regression, you can think about it either in terms of the function space view, so with Gaussian processes, or the weight space view, which is the kind of closer to classical regression. But so even though the Bayesian linear regression is a special case of a Gaussian process for a particular choice of fixed basis functions, solving the problem in one way is going to have different computational costs than solving it the other way. So it's important to be able to take into account the trade-off in the computational complexity in both of those things, depending on the size of the training data set that you're working with, as well as the number of fixed basis functions that you have in your model. All right, so that brings us to the end of lecture 9. We'll see you back here for lecture 10, where we'll be moving on to decision trees. Okay, thanks for your attention.